Hello, this is Mrs. Ward. I'm going to be doing the notes today for section 5.5, limits at infinity. So what we're going to do today in this section is we're going to determine the finite limits at infinity. So we're still going to go to infinity. So we're going as far as to the right as we can, as far as to the left as we can on the graph, but it's going to approach a singular number. Then we're going to determine the horizontal asymptotes depending on the graph of the function. And we've done this before. We're just going to review this. And then we're going to determine the infinite limits at infinity. That means when I take the limit as x approaches infinity or x approaches negative infinity, the answer is also going to be infinity or negative infinity. So let's go back and review. So if I have this, if I have the following equation and I want you to find the limit as x approaches the positive infinity, and this is this one right here. That means as the graph goes further and further right. So that's me going further and further right. When x approaches negative infinity, that's asking me what's going on as the graph approaches further and further left. Some people like to call this end behavior. So it's what is the graph doing at the end? So as far to the right or as far to the left. So there's three ways we can do this. We can do this graphically, numerically, and algebraically. So the first thing we're going to do is we're going to look at the graph. So if I graph it on my calculator, here's the graph that I did on my calculator. As I look here, as I go further and further right, it looks like the line almost flattens out. Since I count, there's 1, 2, 3, 4, 5. So graphically, I'm going to say the answer to this one, as x approaches positive infinity, is going to be negative 5. If I do to the left, so negative infinity, it looks like the graph does the same thing, count 1, 2, 3, 4, 5, and it looks like graphically this one is going to be negative 5 as well. So that's how I do it graphically. I look at the graph. Numerically means, hey, let's make a table. We've done these tables before. So if you haven't graphed this function in your calculator right now, you're going to pick up your calculator and you're going to put it into a graphing page. So I'm going to control divide. And I'm going to do negative 5x squared over x squared plus 1. And I have this graph, which I already had, but now you all have it. And then I'm going to complete this table. So I want the table at negative 50, negative 10, negative 1, 1, 10, 50. So I'm just going to crank through just to remind you how to do that. You hit menu, trace, and then graph trace, and then if I start with, let's say, negative 1, I get negative 2.5. If I do negative 10, remember, once you have that spider, you just keep on taking in the numbers. Negative 4.95, and then negative 50, I get negative 4.998. So here, and I've already done the ones, so you can do those if you haven't done those. And it is an even function, so they are going to be the same. So remember, in order for a limit to exist, it has to be appearing to approach the same number, and it does. This is me getting larger and larger to the negative, so I'm going to be consistent. So that's still going to give me that negative 5. This is me getting larger and larger numbers to the right, and that's going to give me negative 5. If you weren't sure and you want to go say negative 1,000, eventually your calculator is going to make that. Your calculator is going to write it down as negative 5. It's just depends on how many digits your calculator can hold. So that's numerically. Algebraically says, well, I remember when I look at this, and I'm going to copy this down here again. If I look at this, I know that this has a degree of 2. The numerator has a degree of 2. The denominator has a degree of 2. If those degrees match, it's kind of like I just put those on. And then I simplify. So if I simplify and the x squared simplify, I get negative 5. And that's me doing it algebraically. And that's going to be the same that's going to be how we found our horizontal asymptote. And that would be y is equal to negative 5. and that -5, the horizontal asymptote, is going to be my limit as x approaches infinity or x approaches negative infinity. Remember, not all rational functions have a horizontal asymptote. Sometimes they are slant. So remember, just to review, when we have horizontal asymptotes, we're going to divide the coefficients to the highest power and fill in the 0 with if anything is missing. So like if I have example 1, the highest value I have in my numerator is -x squared. The highest value I have in my denominator is -7x squared. If I simplify this, the x squared would simplify, and I'd be left with -1 over -7, which simplifies to 1/7. So as x approaches infinity, my limit is going to be 1/7. Because my horizontal asymptote is going to be y is equal to 1/7. We've done these before. I didn't think I read this, but horizontal asymptotes determine the end behavior of a rational function, therefore may be used to find its limit at infinity. So when I find the horizontal asymptote, which remember we learned there's 3 things to do to find the horizontal asymptote, that is finding my end behavior of my limit as x approaches infinity. So here I'm going to do another one. This time x is approaching negative infinity. I'm going to start off the same way that I just did that other one. I'm going to take the highest power that I have in the numerator, which is -x to the third, and the highest power that I have in the denominator, which is x to the fourth. If I were to simplify, I would end up with -1 over 8x. Well, as x gets smaller and smaller, that's going to be like -1 divided by 80, and then 800, and then 8,000. So as this happens, as the rate closer and closer to 0, so my horizontal asymptote is y is equal to 0. What we said before is if the degree of the numerator is 3 and the degree of the denominator is 4, if the degree of the denominator is more than the degree of the numerator, it's always going to have a horizontal asymptote of y is equal to 0. Since my horizontal asymptote is y is equal to 0, then its limit as x approaches negative infinity is also going to be 0. Limits at infinity have the same properties as limits discussed in section 3.3, which is what we did earlier in the year. So if R is a positive rational number, C is any real number, so you're dividing a constant by a larger and larger number, it's going to be 0. If x to the R is divided by when x is less than 0, so this is going to be a negative number, it's also going to be 0. So example 2, I'm trying to limit as x approaches infinity. So remember, when we talk about limits, we could separate them into like a section by a section. So when I do this, I'm going to think of this as a limit as x approaches infinity of 2 over x to the third minus the limit as x approaches infinity of just 3. So if I do that, then this is going to be my constant divided by a power, that would be the c over r, that's going to be equal to 0, so I'm going to have 0 minus, and then even though this is infinity, I can't put anything into it, like there's no x, so it's not going to get larger, it's not going to get smaller, it's just going to stay this 3, so I'm going to end up with 0 minus 3, which means my whole limit is going to be -3. So let's look at b. So b, I'm going to separate again, so I'm going to take the degree of the numerator is 1, the degree of the denominator is 1. So I'm going to take that 4x over 9x, think of it as though those x's simplify, and I'm going to say that the limit as x approaches negative infinity is going to be 4/9, because my horizontal asymptote in both directions is going to be y is equal to 4/9. So that matches the end behavior, which means it matches I wanted to, which I didn't. I could have also done like -1 divided by 9x. And the constant divided by a variable is still equal to 0, so I did not bother to write that. Okay, the next one, limits at infinity may also be found by dividing both the numerator and denominator by the highest power of x in the denominator. So what that all that is saying is that if I take everything and I divide it by x squared, so I could take 1 over x squared, because that's the highest power in the denominator, minus 3x squared over x squared. And this would be x squared divided by x squared plus 2x divided by x squared minus 5 divided by x squared. So I just divided every single thing in this by x squared. So a constant divided by x squared would be 0. These will simplify, and I'll be left with -3. Well, 0 minus 3, -3. This x squared divided by x squared would be 1 plus x divided by x squared. This power is higher, so that would be 0 minus, stopping that sign now, a constant divided by a power, 0. So I'm going to end up with -3 over 1, so that is going to be -3. That is my horizontal asymptote. My horizontal asymptote is y is equal to -3, so this limit will be -3. Again, what we learned to do is take this -3x squared divided by this x squared. Everything else will be 0, and I'll end up with -3. I feel like sometimes we're making this a little bit harder, but this is why we're making it harder. Functions that are not rational might have a different right and left horizontal asymptote. So this one, since I have that radical in the denominator, it's going to change the way my graph looks. So when I have x approaches infinity, this means I'm looking towards the right. So when I do this, the degree of my numerator is 1. The degree of my denominator is also 1, because if I take the square root of 2x squared, the square root of 2 times the square root of x squared, that would be the square root of 2 times x. So it has a degree of 1. If I did it the same way I did before, I would have 3x over the square root of 2 times x. These x's would simplify, and my horizontal asymptote would be 3 over the square root of 2. That would be my horizontal asymptote. Of course, I would never leave it like that. I would say y is equal to 3 times the square root of 3 over 6. Oh no, I did that so wrong. Why did I do that so wrong? I don't know. Square root of 2, this is 4, duh. So this is, and then this is 2. Woohoo! So that would be my horizontal asymptote. Now, that's to the right, that matches, this is good. So this would be 3 times the square root of 2 over 2. But there's a little hiccup, a little problem. When I take this x squared, when I take a number and I square it, it always becomes positive. So I can always take the square root of that x squared that's in the denominator. The problem is if this is going to negative infinity instead of positive infinity, this 3x would be getting smaller and smaller, so it would be a negative number. And I think we have an example of that one coming up. Yeah, we have the same problem, the exact same problem. I thought I had it somewhere. Wrong thing. Oh yeah, there it is. I have the exact same problem, but it's going to be as x approaches negative infinity. So when I have this negative infinity, like I'm going to take the square root of 2 times some negative number, and I'm going to square it. So that's going to be positive. So like it's kind of like I'm putting a negative x in there instead of just a positive x. So this would be negative 3x. This, when I take this negative x and I square it, that would be negative 3x. And this would be the square root of 2 times x squared, because a negative number squared is a positive. So this will become the square root of 2 times x. And now this one, the horizontal asymptote is going to be y is equal to negative 3 squared to 2 over 2. So this one has a different end behavior than when I go to the right and when I go to the left, they have different end behaviors, because when I take the square root of a negative number, that's going to be, when I take the square root of a negative number squared, this denominator is going to be positive, but when I take that, put it in the numerator, it's going to be negative, so my answer is going to be negative if it works out like that. All right, infinite limits at infinity. So that's the graph goes to positive infinity or negative infinity. So your graph is going to go up, 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 or down, down, down as you go left to right. So if I have this graph of x to the third plus 2x squared minus 1, let's say I didn't know what was going on, so I wanted to graph it. So I'm going to add a graphing page to my calculator. I'm going to do x to the third plus 2x squared minus 1. Now, if I want to find, if I let my graph does that, so I'm just going to sketch that so I have the visual. So it goes like this, which I should have known the whole end behavior from algebra 2. As x approaches infinity, this graph is going to go up, up, up. So this whole limit is going to be positive infinity. I'm not going to reach a certain number. I'm not going to have a horizontal asymptote. So as the x values get larger and larger, the graph is going to get larger and larger. Now, it doesn't ask. I'm just sort of adding it here. But if I did the same thing, same equation that I have there, x to the third plus 2x squared minus 1, and I want x as x approaches negative infinity. Now, instead of going to the left, instead of going to the right, I'm going to the left, and that graph goes down, down, down. So this is going to be negative infinity. So that's what it looks like when you have a limit that is an infinite limit. That means you're going to approach positive infinity or negative infinity as you go to the left or the right. And then just remember, we talked about even and odd functions. So if your degree is even, that means you end both up. So like the parabola is even, or you end both down. This happens when my lead coefficient is positive, and this is what happens when my lead coefficient is negative. And then the one that I just did was a degree odd, because the one I just did was raised to the third power. My lead coefficient, that does something like this. This is if my lead coefficient is positive. And it goes something like this. If my leading coefficient is negative. So you should remember those from algebra 2. All right, rational functions without a horizontal asymptote. So remember, we also talked about this when I look at the numerator, it has a degree of 2. When I look at the numerator, it has a degree of 1. So the degree of the numerator is 1 more than the degree of the denominator, which means I have no horizontal asymptote. But because this is exactly 1 more than this, I have a slant asymptote. And we've done this before. So in order to find the equation of the slant asymptote, I take 4x minus 2x squared. Actually, I want to rewrite that as negative 2x squared plus 4x. I like having my highest powers in front. And I'm going to divide it by x plus 1. Then I ask myself, and I should only have to do this 2 times. I ask myself, would I have to multiply by x by negative 2x? And you tell me negative 2x squared, and you tell me negative 2x. So negative 2x times this x is negative 2x squared, and negative 2x times this 1 is minus 2x. Then I'm going to subtract. So 2x squared minus 2x squared would be 0. 4x minus the negative 2x would be 6x. There's nothing written here, so I'm going to add plus 0. I'm going to bring that 0 down. Ask myself, what do I add x? What do I have to multiply x by to get 6x? And you say 6. So this will be 6x plus 1. And subtract. And we end up with negative 1. It doesn't really matter what that remainder is. This is the equation of my slant asymptote. So my slant asymptote has an equation of y is equal to negative 2x plus 6. So I could actually graph it, I could think about it. What I do know is It's a graph that looks something like this. I know as I go to the left, it's going to go down. I'm sorry, as I go to the right, it's going to go down. As I go to the left, it's going to go up. This is as x approaches negative infinity. So this graph is going to go negative infinity this way, which means this graph is going up. So my answer is going to be positive infinity. So we did those before. We did slant asymptotes. I hope this helps, and I'll see you next time in class.